Welcome back, AP Statistics students. This is Chapter 25, Part 2. We're going to be talking about the test for homogeneity. So as we've seen in our last section of Chapter 25, Part 1, the goodness of fit test compares observed counts with a theoretical model, which we refer to as the expected counts. Okay, so moving on with that way of thinking, a very similar process can determine whether or not a distribution of counts is the same among different subgroups of the population. This is called a test for homogeneity, and that just means sameness, which is another chi-square test. So what would be an example of that? For example, a test of homogeneity could tell us whether the distributions of post-grad choices are the same regardless of which college students attend and vice versa. Okay? So a test for homogeneity could help us determine, well, is there a difference between going to the College of Agriculture, Arts and Sciences, Engineering, or ILR, which is Industrial Labor Relations? Is there a difference among those students in each of those colleges in terms of what their post-grad plans are? In other words, is it more likely for people in agriculture to go right into employment than for arts and sciences? Or is the distribution of the post-grad choices the same regardless of which college you're going to? Okay, so that's a good question. That is a homogeneity question, and we'll be using a test for homogeneity to determine that in just a little bit. So all the same assumptions and conditions for goodness of fit apply that is, for a test of homogeneity. We need our data to be counts. We need independence, which we can check via randomization in the 10% condition. And the expected cell count must be at least 5 for each cell. All right, so all the same as before. The chi-square test statistic, which you occasionally need, is computed the same way as with the goodness of fit test. The test statistic is the sum of the observed minus expected squared over expected, all right? And observed and expected we get from our two-way table up here. For example, the observed value for agriculture and employed, that intersection would be 209. The expected value would be 685 out of 1456, so that's our proportion of folks who were employed on the whole, times the number of people who were in agriculture. So it would be 685 divided by 1456 times 448. Another example of an expected count. Let's look at arts and sciences and grad school. That 171 is our observed count. The expected count would be 466, that's the total number of people who are in grad school, divided by 1456, our grand total, times the number of people in arts and sciences. That would be the expected count. So we would do observed minus expected for each cell, square that, and divide that by the expected for that cell. Sum them all up, and you got yourself a test statistic. Per the norm, the p-value can inform us as to whether to reject H sub 0 or not, all right? And we'll see how the test statistic and the p-value are related specific for the chi-square test a little later on. Okay, so let's get started in answering this question. So the null hypothesis would be the distribution of post-grad choice is the same for each college, all right? The distribution of post-grad choice is the same for each college, okay? So what that's saying is that it doesn't matter which college you go to, the same proportion of people are going to be employed, going to grad school, and doing something else, okay? The proportion's not going to change as you go from college to college. They are homogeneous groups, these colleges, in terms of the distribution of post-grad choices. Alternatively, the distribution of post-grad choice is not the same for each college, all right? So that is the alternative hypothesis. These are not homogeneous groups. Being in one college makes you more likely to be doing, I don't know, this than that. To find the right chi-square curve, we need to know the degrees of freedom. So for the test for homogeneity, the degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. For example, our table to the right from our textbook has 3 minus 1 times 4 minus 1 equals 6 degrees of freedom. In the cells, not including the margins, we exclude the margins in the calculation. So looking at these cells, we have 3 rows and 4 columns. So it would be 3 minus 1 times 4 minus 1 equals 6 degrees of freedom. All right, let's get to the problem itself. We have our hypotheses down. The distribution is the same as the null. Distribution is not the same as the alternative. So our data need to be counts. We also need to be able to assume independence. That's where things get a little shaky. We'll get into that in just a moment. Expected cell frequency condition. The expected values are all at least 5. All right? And it says shown below. It's obviously not shown below. You're just going to need to trust me on that. They're all at least 5. Okay, so what about this independence thing? Even though this is not a random sample. Okay, so randomization is a clear no. Student plans should be largely independent of each other. Okay, there you go. It's an assumption. The occasional friends who join TFA together or college couples who make grad school decisions together are too rare to affect this analysis. Okay, so very much an assumption. Also, we don't need to show randomization or 10% condition for this particular case. Note the scope of our study. All right, we're making a statement about one graduating class at one university. All right, so this is not going to be broadly applied. We can kind of skirt the rules a little bit on this one. If this were being applied more broadly, we would want to go more by the book. All right, so there you have it. We take these results with a grain of salt and acknowledge that we're only applying them over a small scope. All right, so at this point, we would want to use the matrix feature in the calculator. You can get to that with second matrix edit. The matrix of expected values is automatically computed. That is a huge time saver. I do not feel like computing 12 different expected counts. That's ridiculous. Our calculator can do that for us, and it will. Then we're going to use chi-square test to find the p-value. All right, not chi-squared GOF test like last time. This is just chi-square test, right? We can also find the test statistic to pair with our p-value. That's good for free response problems and the occasional multiple choice problem that has us find a test statistic, and summarize the conclusions in the context of the problem. Okay, now that we're at the calculator, we're going to go to second matrix. Okay, now I've already made this matrix, but I want to show you how to set one up. We're going to go over here to edit, and I'm just going to start off with matrix B here. All right, we see that we have a 1 by 1 matrix. All right, now this first one that my cursor is on, that refers to the number of rows. This one right here refers to the number of columns. If you recall, I have 3 rows and 4 columns. So I would say let's make this 3, hover over this, and make that 4. Okay, and we hit enter. Now we have a 3 by 4 matrix, and then we enter our observed values. Now I'm going to go back here because let's go to a second matrix. Let's go back to A, and we're going to see how A looks. I already input these values just because I don't want to waste your time inputting them. And now that we have matrix A, we are good to go. So what I'm going to do now is go to a familiar place. We're going to go to stat. We're going to go to over to tests. And right near the bottom is chi-square test. All right, that's right next to chi-square GOF test, but chi-square test relies on matrices, okay? So we have the observed is A, expected is B, and we are going to hit calculate. All right, and we have a chi-square statistic of, oh my goodness, that is a wild value right there. And the p-value is e to the negative 18. Yeah, we got an issue right here. We are definitely rejecting that null hypothesis. It really does matter which college you go to. the post-grad choices are going to be quite different. So how do we interpret these results? The p-value is very small, so I reject the null hypothesis. What's my conclusion? There is sufficient evidence that the post-grad activities of students from these 4 colleges do not have the same distribution. So now we need to talk about examining the residuals for a two-way table, because just like with a goodness of fit test, if we reject the null hypothesis in a test for homogeneity, as we just did, we probably want to confirm which cells are making us do that, which cells specifically are defying our expectations. And spoiler alert, there are many cells that defy our expectations. That's why we had some serious scientific notation in our p-value. As before, we can standardize the residuals to find out, okay? So standardizing residuals gives us an idea of how far each count is away from what we expect. Now, what does that mean precisely? Precisely, it means the number of standard deviations an observed count is away from its corresponding expected count. So we standardize, that means that our units are standard deviations, and we see how many standard deviations is an observed count away from its corresponding expected count. So for each cell C, let's just call it, the standardized residual is the observed minus expected divided by the square root of expected. And yes, that is the square root of a component, all right? That is the square root of a component, all right? And the only difference is that the value C can be negative, but if you were to square it, you would get a component for a cell, and we discussed what components are in the last video. Standardize the cell at the intersection of agriculture and employed. So we are tasked with standardizing that one cell, saying how many standard deviations is our observed count away from the count we would expect to get if the null hypothesis were true. All right, so let's put up the answer. The observed count for that cell at the intersection of agriculture and employed, if you recall, is 209. The expected count is 685 divided by 1456. That is the proportion of folks who were employed times 448. That's the number of folks in agriculture. So it's the expected proportion of the people in agriculture, or the expected number of people in agriculture, I should say, who are employed, all right, right out of college. And that number is very close to 209. And that is one of the rare instances in which the number that we observe is frighteningly close to what we expect. There are a lot of instances in which that is not the case, as we will see very shortly. But that's going to be 210 and change. So the standardized residual would be my observed count minus my expected count over the square root of my expected count, which is negative 0.12 and change. All right, so it's this many standard deviations away from my expected count, my observed count would be. So here are the rest of the standardized residuals, and as you can see, there are some that really stand out. So below we have these standardized residuals for the two-way table involving colleges and post-grad plans. Naturally, the most extreme residuals stand out, all right? So if we're thinking normal model, we're thinking 68, 95, 99.7 rule. Within 3 standard deviations, we have almost all of our data, okay? So when we see values like the intersection of agriculture and grad school, which is past 3 standard deviations below what we expect, and then we see other past 4 standard deviations, now you're talking about no man's land, 4 standard deviations, that's slim pickings out there. A lot of these are well past 1 standard deviation. This one right here, I think, takes the cake. engineering and other was way off what we would expect if the null hypothesis were true. All this to say, our alternative hypothesis is definitely the best option of the two. This null hypothesis is toast. There is no way that these colleges are homogeneous in terms of their respective postgraduate plans. They're totally different. So, for example, industrial labor relations, as I mentioned before, seem extra likely to be employed out of undergrad. All right, so industrial labor relations, yeah, that's past 3.5 standard deviations too high. They do seem especially likely to be employed out of undergrad. All right, well, engineers seem to find their way to grad school. So here they are, a little bit past 3.5 standard deviations as well. All right, so we see that engineers are especially likely to end up in grad school. All right, so tables of residuals like this can help us see where we can point to say, yeah, that's where the null hypothesis went wrong.